Welcome. In this session, we'll talk about filtering noisy signals in MATLAB. Let's start. Now, in order to illustrate the concept of noises, remove noise from noisy signals in MATLAB, let's start with a basic signal like sinusoid. We know a sinusoid is a signal of single frequency. For example, if we look at the Fourier transform of a sine wave, Fourier transform of a cosine 2 pi f naught t is shown here. This shows simply there are two impulses, one at minus f naught and another at plus f naught with amplitude a by 2. Okay, and both cosine wave and sine wave are referred as sinusoids. There's only one difference between sine wave and cosine wave, that's there the phase shift of 90 degree or phase difference of 90 degree. Now, if we look at the plot of this Fourier transform of this cosine wave, we have plotted the magnitude here. You can see there is only one frequency present in the signal with value f naught. Now remember, when we compute the frequencies of a signal from magnitude spectrum, we only consider the frequencies which only positive frequencies are taken into consideration. Okay. All right. So the frequencies present in this signal is simply f naught. So this signal is a signal of single frequency that we already know. Cosine wave is a signal of single frequency. That's what the Fourier transform shows. Now, in order to illustrate the concept of filtering here, what we are going to do, we are going to create this sine wave first, then add noise to it. Okay. After adding noise to it, what we are going to do, we are going to design a filter with specific characteristics, and we are going to use that filter to remove the noise from this sinusoid. Okay. So let's switch to MATLAB and create this sinusoid. So let's call this the desired signal. So this is our desired signal. Let's suppose the time duration of this desired signal is from 0 to 1. Okay. So t is an array from 0 to 1, or for us, t is simply the time axis from 0 to 1. Okay. Now a desired signal, let's call it x. So x is 20 sine of 2 pi 10 t. So x is a sinusoid with amplitude 20 and frequency. Yeah. Now if you look at what we just created here, so let's check what we just created. So you can see this is a sinusoid with amplitude varying from minus 20 to plus 20, frequency 10 hertz, and time duration of this signal is from 0 to, okay, this is what we created. Okay. Now next, what we are going to do, we're going to add noise to this signal. So we are going to create a noisy signal. So let's call that x of n. So x of n is x plus, let's suppose 10 times sine of 2 pi. Let's suppose the frequency of this noisy signal is 200. So, okay. So this is our noisy signal. X of n is our noisy signal. So what is this noisy signal? What are the frequency components in this noisy signal? We know sine is a signal of single frequency. So one frequency present is 200, and another frequency present will be the frequency present in x. What is the frequency present in x? That's 10. So the two frequencies present in this noise are 10 and 200 hertz. Let's plot this noise signal as well. Let's see what we created. What is this noisy signal? So you can say this is the noisy signal. This looks very weird. So this is the noisy, and that's what we created so far. So we created the desired signal and a noisy signal. Let me plot these desired signal and noisy signal on a single plot. Let's say subplot 511. Why subplot 511? Because we are going to plot various signals. So I will say t comma x. Let's also use color red here and say the line width is suppose 2. And let's put the title as well here. So title is desired signal. So this is our desired signal. All right. And now what we are going to do, we're going to copy this code. So we're going to paste it here. So we'll say 512. What is the name of our noisy signal? So this is our noisy. So now if I plot this, you can see this is our desired signal. Now on this, we are going to have one more plot, that is, okay, this is our noisy signal. Okay, this one is our noisy signal. Now let me fit this, fit the axis to this plot. So for this, what we are going to do this, what we are going to use, we are going to use axis right function. So this will fit this noisy signal to on this plot. Okay, you can see the amplitude of this signal is minus 22 plus 2. So this is our desired signal and noisy signal. That's what we have created. So next, what we are going to do, we are going to do the frequency domain analysis of this noisy signal. Now, how do we do the frequency domain analysis? By computing the Fourier transform or discrete Fourier transform of this signal. Now, if you look at the discrete Fourier transform of a signal, this is the discrete Fourier transform of a signal. Okay, x of k is 1 by n, summation k running from 0 to n minus 1, x of n e to the power of minus j 2 pi k n. Okay, this is the formula of DFT of a signal. Okay, so how do we compute DFT of a signal in MATLAB? So in MATLAB, what we do, we use FFT function. So we use FFT function to compute the DFT of a signal. Now, FFT in theory means fast Fourier transform. It's an algorithm to compute the DFT of a signal. In MATLAB, it's simply a function to compute the DFT of a signal. So what we'll do, we'll compute this by storing the DFT in this. So FFT is the name of the function. Say FFT of x of n. This will compute the DFT of x of n and store it in capital X. Now, as you can see from this formula, x of k is complex function. So what, in order to plot the result, what we are going to do, we are going to compute its magnitude. How do we compute the magnitude of a function in MATLAB? We use ABS function. So this will give us the magnitude of this DFT. Okay, next. If you look at the DFT of the sine wave, there are two impulses. One is at minus f naught, another is at plus f naught. But if you look at the formula of DFT, it starts at k equal to 0. Okay, that means it starts at k equal to 0 and towards infinity. So how do we shift half of the frequencies on the negative side? So for this, MATLAB has an inbuilt function that's called FFT shift. And this FFT shift is half of the frequencies of this DFT on the negative side. So what we have done so far in this 3 steps here in the DFT steps, we have this FFT computes the DFT of the signal and stores in capital X. Then we compute the magnitude of this DFT because FFT is the complex function. Then we have shifted half of the frequencies on the negative side of this frequency spectrum by using FFT. Now we can compute all these 3 steps in one line. So we'll write here FFT shift. Then we compute ABS and then this. So this will store the FFT. So we can remove these 2 steps because all the 3 steps are computed here. So first, this computes the DFT of the signal. Then it computes the magnitude of that DFT. Then lastly, we shift half of the frequency on negative side. Now, if you look at the formula of DFT, there's also 1 by n. So how do I insert this 1 by n here? What we are going to do, we are going to check number of points in the noisy signal. How many points are there? We're going to store that in capital N by using the length function of that. So this simply computes the number of points in x of n and stores that in. And we are going to divide this capital X by this. Okay, this is the formula of DFT. Okay. All right. Now, once we have computed DFT, we'll plot this. Now, in order to plot this, we need frequency axis. Now, in order to create the frequency axis, we'll say f is equal to length space. And we are going to say n by 2, comma n by 2, comma n. Okay. So what is this length space n minus n by 2 plus n by 2 to n does? It will create an array from minus n by 2 to plus n by 2, and the number of points in that array will be n, and that will store in n. So this is our frequency axis. For example, if I say n is 1000, so this will create an array from minus 500 to plus 500, and the number of points in this will be 1000. Similarly, if I say n is, for example, if I say linspace 0, comma 5 and 100, so this will give me an array from 0 to 5 with 100 points. Okay, that's the meaning of this. So next we are going to plot this. So let me copy this line here. So we'll say, so we'll say subplot 513. So subplot 513 plot of capital X, and this is DFT noisy signal. So this is DFT noisy signal. Now you can see the result. Okay, you can see there are two frequency components. So let me change the color to blue. Okay, let's change the color to blue. You can run this section. You can see the result. Now you can see there are two frequency components. One is here, another is here. Again, remember only first two frequencies are counted when we compute the frequencies of the, consider the frequencies of a signal. Okay, if you look at the value of this signal, you can see x-axis value is 10. That means this has x-axis is 10 value. So frequency of this is 10. Similarly, if I put the cursor here, you can see the frequency x value is 200 and the frequency of this component is 200. So we already know that the frequencies contained in this is 10 hertz and 200 hertz. So we already know that from here that x of n is composed of desired signal and a noise component that has frequency of 200 hertz. That we already knew from this. Okay, and DFT gave us the proof. Next, what we are going to do, we are going to filter this. So we are going to do the filtering here. So filtering. So for this, what we need a filter. So let's design the filter. Now MATLAB has an inbuilt toolbox that's referred as FD tool. If you run this on command window, a window will pop up that looks like this. Now you can see on this, you can design different types of filters. Okay, low pass, high pass, band pass, IIR, FIR. Let's design an FIR filter by using windowing technique, and let's specify the order. Let's suppose order is 10, and let's use a rectangular window. Okay, now what's the frequency of our desired signal? 10 hertz. What is the frequency of our undesired signal? That is 200 hertz. So let's say the cutoff frequency is 50 hertz. Okay, let's say cutoff frequency is in between, that's 50 hertz. Okay, this then when we click the design filter, this is the magnitude response of this filter that we design, that is of order 10 and cutoff frequency is 50. Now you can check the different properties of this filter here. This is the phase response. This is the impulse response of that filter. This is the step response. This is the pole zero map. And these are the options of that FIR filter that we just designed. Okay. Now what we do, we have designed this filter. We're going to export it. Now if I say export here, let's export this as object, and name of this filter will be HD. So check this override variable box, and we're going to export. Now you can see there is one HD variable appears in the workspace window. You can check it here. It is here. Okay. Now we are going to use this. Okay. Now how do we use this filter? MATLAB has an inbuilt function to filter signals. Okay. Let's store the signal in X of R, that is recovered signal. And for this, we're going to use to filter the noisy signal. We're going to use MATLAB's inbuilt function, that's filter. And we're going to use HD to filter X of M. So we'll do the filtering of X of M using the filter that we designed. Okay. Now, okay. So once I run this section, the result is the filtered signal is stored in X of R. Let's see how good as the signal filter. Okay, so in order to plot this, let me copy this. Control C. Let me paste it here. So we're going to call it 514 T versus X of R, and this is the recovered signal. This is our recovered signal. Okay, let me run this. Okay, this is the recovered signal. Although not very clean, but very close to the results. Not 100% clean. Okay. Now, before I design a different filter and try to completely remove this noise, let's do the DFT. Let's compute the DFT of this recovered signal. Okay. For this, what I'm going to do, I'm going to copy this part of this code. And we're going to say this will be the DFT of recovered signal or filtered signal. Okay, let me say filtered instead of recovered. Filtered signal. So we'll store that in X of R, and our recovered signal is stored in X of R. All right. So now this is the DFT of this. Now I'm going to copy this piece of code from this. I'm going to paste it here. Okay. We'll say this is 5-1. What was the number of supply? 515. So 515 F versus X of R. Let's change the color to T. Okay. And this is DFT of recovered signal or filtered signal. Let me use filtered. Filtered signal. Now we'll run this section. This is the DFT of the filtered signal. You can see there is little amplitude of this tone and frequency is still present here. Very little mild. That's why this looks like this. Okay. Next, what we are going to do. So this is our filtered signal, and this is the DFT of the filtered signal. So there's some contribution of this 200 hertz frequency still present in this. Next, what we are going to do. We are going to here we are going to design a different filter such that we are able to remove more noise from this. Okay. For this, we are going to go back to the filter designer tool. Let me change the order simply to 50. Let's see what will happen. Okay. So order of this filter, FIR filter is now 50. Okay. Rest of the properties are same. We are not changing the rest of the properties. So we are going to export it again. So export it. Now I am going to run the code again. So rerun this section. Run this section. Let's see the result. What happened? Okay, it's more clear. So if you change the properties of this filter, you will see the result will be better. Okay. So this is how we remove the noise of a signal in MATLAB. So first, what are the steps that we perform? We created the desired signal. Then we added noise to this desired signal, created a noisy signal. Then we computed a DFT of this noisy signal that gives us the frequency components present in the signal. In this example, we already know the frequency component. Now imagine if this noisy signal is a voice. Okay, you want to filter the noise. Okay, so you will compute the DFT. You will check what are the frequency components present in the signal. Okay, that's the step. Next, you are going to design a filter and pass this this noisy signal through this filter by using the MATLAB's inbuilt function. That's the filter function, and then check if the noise components, frequency components are completely okay. You can see this is very close to this. This recovered signal is very close to the desired signal. This is how we do the filtering in MATLAB. I hope you understood. Now, what's the application of this that we just? So, for example, imagine this here. This noise is not what you did here. That's how you created it. Imagine this is your voice that you want to filter. Now imagine this is an image. Okay. And this is an image. Okay. You loaded that image here. Then we computed the DFT, check the different frequency components of this, see which noise components are introduced in this, and pass it, this noisy signal through the filter that you designed, and check its properties. Then see if the filter is removed or no. This is how we remove the filter from a signal in noise, and this is how we design a filter. You can design any type of filter here. You can design IR filters. There are different types of IR filters available here that you can use. There are different types of FIR filters that you can use. You can also design a low pass, high pass, band pass. Okay, there are different types of filters that you with different properties here. Okay, you can specify the order. You can specify the other properties of the filters. That's why MATLAB is very powerful in image processing and especially in signal processing applications. Very powerful. Okay, you don't have to do anything. You don't have to compute the order and other these calculations. You just specify the desired properties. MATLAB will give you the filter. Okay, let me stop here. I hope you understood the concept.